Hello, class. Welcome to lecture 10. Today we're talking about binomial probability distributions, which have a very fancy sounding name, but they're going to turn out to just be like a very special situation of these charts that we've been learning about. Okay, so let's just jump right into it. So we're going to create a question, and from this question, talk about what we want to talk about. So let's think about a situation like this. So consider a probability experiment where there are only two outcomes. So the two outcomes are always going to be called success or fail. Now it's up to you to decide what a success is and what a fail is, but that's always what it's going to be. So for example, of something like this, I could shoot a free throw. So then I either make it or I don't. So there are only two outcomes. And so making it, typically you would call that the success, unless you want to be really strange for some reason, and missing it you would call the fail. Notice that it's not necessarily a 50-50 chance, right? I'm very bad at basketball. So it's not like automatically 1/2 probability of success and 1/2 probability of fail. For me, it would be very low probability of success and high probability of fail. It would not just be 50-50. But there's lots of other examples. So some sort of machine doing a task. So printing or something. So either the copier prints or it doesn't, or a car part working or it doesn't work. Stuff like that. So a lot of things can be thought of like this. So a more familiar one that we've been dealing with, coin flips. So you could think of a coin landing on heads as a success. And if it doesn't land on heads, then you call that a fail. So success is it does do that, and fail would be that it does not. So this one is 50-50. The success and fail are both 50% chance, 1/2 probability, but it doesn't have to be like that. Okay, so then what we do, we have our probability experiment with just two outcomes, success or fail. So then, whatever your experiment is, we repeat it some amount of times. Experiment, some amount of times. So you can pick that ahead of time. It could be like 10, 30 times, 4 times, whatever you want. So I could shoot 4 free throws, for example. Or I could try to print 20 times. Or I could flip 15 coins. So then the idea is each time I'm doing it, I'm thinking about if I'm succeeding or failing. And then I want to look at probability of that happening. Okay, so then we look at the probability of a certain number of successes. So if I shoot 4 free throws, maybe I want to know what's the probability of making 2. or probability of making 3 or 1 or all 4, stuff like that. If I print 20 documents, what's the probability that 15 of them actually print and 5 don't? So the nice part is we're going to figure this out just by knowing the probability of one success. So let me write it like this. So we'll figure it out from knowing just the probability of one success. Okay, a single success, I should say. So let's do it with the free throw example. So what's the probability that I make about three free throws from 4 attempts? And so when I say questions like this, I'm always going to be secretly using the word exactly. So exactly 3 free throws, not. So for making all 4 does not count, just exactly 3. So what's the probability of doing this if, I got to finish the question, if my probability of one success, aka making 1 free throw, is, I don't know, pretend I'm actually decent, 7 out of 10. So if I know that if I just do it once at any one time, my probability of making it is 7 out of 10, then using that, what's the probability that I can make exactly 3 if I tried 4 times? So these are the relevant pieces of information here. Okay, so this is an example of something called a binomial experiment. So let me say that is before we tackle this problem. Binomial experiment. So what that means is that you have a fixed number of trials. That's how many times you do the thing. So in this case, that's 4, because I'm trying 4 free throws. The outcomes are independent of each trial. So what does that mean? Well, remember that independent, that actually means something important. That means that they don't affect each other. So what this is saying is I have to assume that making 1 free throw or missing 1 free throw doesn't affect my chances of missing or making the next one. They're independent of each other. Any one throw does not affect a different throw. And then there's got to be the 2 outcomes per trial. That's the success or fail. In this case, it's making it or missing it. And the probability of success has to just stay the same per trial. So in this case, in each individual trial, the probability is always 7 out of 10. Okay, but these are the 4 requirements to be a binomial experiment. Okay, so now what we're going to do is we are going to make a probability distribution dealing with this situation. Okay, so what does that mean we need? We need a random variable. So we can make a probability distribution. That just means a little chart. And to do it, you have to have a random variable, which can be a couple different numbers as those are what our little x's were last time. So our random variable is going to be has to be a number. So it's going to be the number of successes and so in this example, if I try to make 4 free throws, that means I'm doing 4 trials. This means that my random variable can take which values. What can little x be? What numbers can this be? Well, if I'm trying 4 times, I can either make 0 shots, I can make 1, I can make 2, I can make 3, or I can make all 4. So then we create the probability distribution where on the left side is always this little x, which are the possible values that the number of successes could be. So since I'm trying 4 times, I can go from 0 to 4. And then next to each little x is the probability of that happening. So again, just to remind you, these numbers are not just randomly there. These represent the number of free throws in this example. Three free throws made in 4 tries. And then over here, we don't know these yet. We're going to figure these out. So now we'll do that. Now notice that this third one here, that's what this question was asking about earlier. What's the probability that I make exactly 3 free throws from 4 attempts if my probability of 1 success is 7/10? That's exactly what this is, finding that. But now we're going to do all 4. Okay, and it's not so bad. The reason we're studying these particular kinds of probability distributions is because they are easier to deal with. And we'll see that right now. Okay, so let's figure these out. That's our next goal. So to begin figuring these out, first notice something interesting that you might remember. If the probability of success is 7 out of 10, then what's the probability of failure? Well, you either do one or the other, right? So if probability of success is 7/10, that means probability of failure must be 3/10 because it's 1 minus 7/10. AKA it's just like the rest of the probability, because it's got to add up to 1 because something has to happen. Either you succeed or you fail. Good. So that's the probability of failure. So now let's start by finding this thing, which was the first one on the list. But just to write it in words, it's the probability of making 0 shots from 4 tries. But you can also think about this as the probability of 4 failures from 4 tries. And what we're going to do is we're going to think about it, because they're independent events, we're allowed to multiply probabilities. Each time I throw the basketball, there's a probability that I make it or that I fail. So let's just think about throwing it once. So if I throw it once, what's the probability of missing? What's the probability of failure? 3/10. So this 3/10 represents that I missed the first shot. But now we know that if I do one thing and then another thing, that the probability of doing them can be found by multiplication. That's what we learned last time, right? So the probability of like rolling a 5 and then flipping a heads, you can figure out by multiplying the probability of rolling the 5 times the probability of rolling a head. So I can multiply by the probability of missing the first shot times the probability of missing the second shot, but that's still 3/10. They're all missing is 3/10. That's the probability of failure in this problem. So this is saying that I missed the second shot. Because they're independent of each other, I'm allowed to multiply. But then this pattern is just going to continue. So now the third shot that I take, I also have a 3 out of 10 chance of failing. So it's the third shot missing. And again, I can multiply because it's independent. And the probability of doing one thing and then another thing and then another thing is just figured out by multiplying them together. And the fourth shot is just another one. So this is the end. This is the probability of missing all four. And so I can write it like this if I want, but it's fine if you don't. I prefer it left separated so you can see where all the pieces are coming from. Right, so let me just one more time explain. So this is really because the reason we can do this is because each throw is independent of the previous one. So we can multiply probabilities of each outcome. And in this case, each outcome is 4 fails. So then what else we can do, and this will help later, is we can sort of write out what it means to fail 4 times using the letter F and writing something like this. So this will come in handy, and what this is saying is that this is saying that like you've failed the first one and the second one and the third one and the fourth one, as opposed to something like we'll see in a second, where if I succeed, I'll put an S. Okay, so that'll come in handy later. It's not so useful yet until you see the other ones. All right, so in any case, this is the probability of 0 successes right here. That's going to go first in our little chart once we fill out that chart. What comes after 0? 1. So now let's figure out the probability of making one shot. But of course, it's one shot out of 4 tries, because that was established at the beginning. You have to establish the number of trials at the beginning. Okay, so then this one is a bit trickier, because what I would like you to notice is that there's only one way to fail 4 out of 4 times. And that's, you just do it. You just fail 4 times in a row. But there's many ways I could fail once. That's the difference. And so that's going to affect their answers. So this can happen 4 different ways. So this is where writing these F's and S's are going to come in handy. So what I could do is I could make the first one. Sorry. Yeah, so I wrote the right thing. Hopefully I said the right thing earlier, but let me just repeat myself in case I didn't. So there's many different ways to fail once. Sorry, to fail 3 times and make it once. That's what I was saying wrong. So I could make the first one, which I'll write as an S. So, and then I could miss the next 3. So this is one way to succeed once and fail 3 times. But I could also instead, I could make the second shot, which I'll write as F, S, F, F. So this is saying that I missed the first one, I made the second, and then I missed the next ones. And now we can sort of see the pattern. And so these are the 4 different ways to make one shot out of 4. So if I'm asking what's the probability of making one shot out of 4 tries, well, I can do it this way, or I could do it this way, or I could do it this way, or I could do it this way. And the key word here is or. this or this or this or this has to happen. And these four ways are disjoint. These are all disjoint events. Meaning if I throw 4 free throws, only one of these 4 can happen at that time. I can't do both at the same time because I can't miss the first and miss the second and still have only missed I can't like make the first and miss 3 and then at the same time somehow make the third one and miss the others. It just doesn't make sense. Only one of these events can happen at a time, so they're disjoint. So we can add the probabilities of them happening to figure out the probability of one success. Because there's only these 4 ways to do it. So if I just figure out these 4 probabilities, I can add them up, and that'll tell me the probability of one success, of making 1 out of 4 tries. And this won't be so bad. Okay, so let's do it. So what's the probability of the first guy? Meaning I succeed once, and then I fail 3 times after that. Well, I'm just going to do what I did before. Because these 4 events are independent, I succeed, then I fail, then I fail, then I fail, I can just multiply the probabilities of each event happening. So what's the probability of success? From the beginning of this problem, it was 7 out of 10. So this is saying that I make the first, just like that's what that S was standing for. And then what was the probability of failure? That was 3 out of 10. So those are then fail 3. Now, so that's the probability of that happening. What about of this one happening instead? Same idea. Well, now I fail the first one, so that's going to be 3 out of 10. I make the second one, so that's going to be 7 out of 10. Then I fail, and then I fail again. So now we can see the pattern. Wherever there's an S, I'm just putting the probability of success. Wherever there's an F, I'm putting the probability of failure. So the next one, and the next one after that, I can get very easily by just doing the same pattern. So the last one is going to be fail, 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 and then finally succeed on the last try. So these 4 probabilities correspond to the probabilities of these 4 different disjoint events happening, of either making the first one, or instead making the second one, or instead making the third, or making the fourth. So then finally, I just have to add all these up. And that's the probability of one success out of 4 tries. It's going to be this giant thing. So I could make the first one and then miss the next ones. Or I could, and that's what I'm adding, I could miss the first, make the second, miss, or I could miss, make it, miss again, and then finally I could miss the first 3, and then make the last one. But if you know some math, these 4 numbers are the same number, because all they are the same 4 things being multiplied together in different orders. So this is really 4 times the same number. So that's the shortcut. If I add 4 of the same thing, I can just multiply by 4, right? So just zooming out here. This, and this are all the same number. because they are the same numbers multiplied together in different orders. Okay, so then this is really the probability of one success. So now we can sort of speed up a bit. So what about probability of two successes? So now I'm making 2 out of 4 tries. Well, the quick way to do it now is list out all the ways to make 2 out of 4 tries. So there are 6 ways. I'll just tell you, give it away. There are 6 ways. I could succeed, succeed, fail, fail, succeed, fail, succeed, fail, succeed, fail, fail, succeed. And then let's see, fail, succeed, succeed, fail, 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 succeed, succeed, fail, succeed, fail, succeed, and that's 6. Those are all 6. So what this means is the shortcut is to realize that the probability of this first guy happening, of making the first 2 and then missing the next 2, is just the probability of making it times the probability of making it times the probability of missing times the probability of missing. But then all 6 of these are the same. So the probability of 2 successes is just 6 times that number. Because there's 6 different ways I could succeed twice and fail twice out of 4 tries. So then, but really it comes from adding all 6 things. So you're really adding this plus the next one, plus the next one, which how we did before, but there's 6 of them and they're all the same. So I'm not going to do that. Instead, I'm just going to multiply the first one by 6 because I already know they're the same. Just because when you switch the order of multiplication, it doesn't change the number. So just for a mini example of what's going on, 7 over 10 times 3 over 10 times 7 over 10 times 3 over 10. That's exactly the same as if I just do the 7 tenths in the front. The order of multiplication, you can switch around if everything is multiplication. Okay, so that's why you can just multiply by 6. So then next is P of 3. Well, I can sort of start skipping ahead. That just means I want 3 successes. And out of 4 tries. And now I sort of see the pattern. It's just every time I get a success, I do the probability of success. So I'm going to have 3 of these and 1 of fails. But then how many ways are there to do this? There's going to turn out to be 4 different ways. There's 4 ways to succeed 3 times. So you can write them out if you want. But they just sort of are the opposite of failing 3 times, which is sort of 2 sides of the same coin. Succeeding 3 times versus failing 3 times are just sort of the opposite. And there was 4 of the failing 3 times, just like there's 4 of the succeeding 3 times. And then lastly, P of 4. Well, there's only one way to succeed 4 times out of 4 times, and that's just do it. You just succeed every time. There's no other way to do it. So if you want, you can put it times 1 just to have it look symmetrically. There's only one way to succeed 4 out of 4 times. It's just do it. 4 S's. Okay, so then this finishes the problem. So now we could write out the probability distribution for this binomial experiment. So I guess I could call it the binomial probability distribution is, so my number of successes that are possible are on the left. So I can do 0, 1, 2, 3, or 4. And we figured all these out. So 0 was just a bunch of 3 out of 10s. Which you can multiply together if you want. 1 is just 1 success and 3 fails. But because there were 4 different ways to do that, I have to multiply by 4. And then there's succeeding twice, failing twice gets me this. And there were 6 ways to do that. And now I'm succeeding 3 times, failing once, 4 ways to do that. And then finally, I'm succeeding all 4 times out of 4. Oops. And there's only the one way to do that. So I'm going to write a times 1, even though it doesn't really matter, just to look sort of proportional. And that's because these numbers are very important, and you might recognize them from something called Pascal's triangle. But if not, that's okay. What I do want you to notice is that these numbers have nothing to do with the probability. Nothing to do with the probability of success. They came from the number of trials. So what this means is, as long as there's 4 trials, that's what dictated these numbers, because they came from drawing out these little things like this. But if there were 5 trials or 6 trials or 3 trials, you would draw a different amount. So what that means is, if I change the probability of success to something else, these 4 numbers would, these 1, 4, 6, 4, 1 would stay the same. So for example, if the probability of success was, say, someone better than me took the free throws and was 9 out of 10, then the binomial distribution, you could fix it very easily. It would be almost the same, because these numbers in red here would stay the same. What would you change? You would just change the successes to 9 out of 10s, and therefore the fails would have to change to 1 out of 10s. And that'd be it. So that's nice. So if I change the number of trials to like 5, though, then these will be a little bit different, and you'll have to figure them out by drawing all the different ways, for example, to succeed once and fail 4 times out of 5. And then you have to draw the rest to figure out how many there are. Okay, but that's for other examples. So now the last thing we want to do with these, the reason that they're so nice, is the following. So binomial distributions, or binomial probability distributions, have relatively simple formulas for the mean, aka the expected value. It turns out to just be n times p, where n is the number of trials and p is the probability of success. So remember how to actually calculate this expected value thing? This bad boy was horrible to calculate. How do you do that? You have to do the x times its probability, and then the next one, and then the next one, and then the next one, all of these multiplied to their corresponding probabilities, and then you have to add them all up, right? It was terrible. That was the expected value. Well, there's a shortcut. If it's a binomial probability distribution, you can just do this. So here, if you did that long giant process, it would turn out to just be 4 times 7 out of 10, because there were 4 trials in that example. The probability of success was 7 out of 10. So it would just be that. So if you actually did the long way to calculate expected value, it would just be horrible. It would take so long. But it would turn out to be the same as just 28 over 10. So you can verify it if you want, or you can believe me. But it's very long. Okay, and the standard deviation was the other type of thing we calculated. Also has a nice formula. It's just the square root of n times p times 1 minus p, aka the square root of the number of trials, probability of success. What's 1 minus p then? That would be the probability of failure. So in this situation, the standard deviation is just going to be square root of 4 times 7 out of 10 times 3 out of 10. So whatever that is in your calculator, that's the standard deviation. And that's way, way, way faster than doing this other giant process. Remember what we did before? Where you like take your expected value, you subtract all the little x's to get their distances, you square them, then you multiply by the probability, all this stuff. Don't want to do that. Whereas this formula, this is just nice and easy. So it'd be, I think, 84 in there over 100. Okay, so that's it for this one, this video. I will see you next time.